Hello everyone, my name is Robert Patlevay. I'm going to explain how current aviation collision safety regulations require pilots to fly too much like boats on a lake. First, I'd like to thank Connie Sampson for her permission to use her boats on a lake photo showing the obvious danger of two-dimensional aviating. The FAA's fatal flaw is the collection of regulations and common practices that funnel level cruising aircraft into thin slabs of legal airspace while wasting all the illegal airspace in between these slabs. This problem should have been abundantly clear in 1956 when two airplanes collided over the Grand Canyon, while both pilots were proudly and accurately demonstrating their piloting skill, flying like boats on a lake at 21,000 feet. This altitude is typical of what is required of pilots flying easterly headings in instrument meteorological conditions on an instrument flight plan. To quantify the FAA's fatal flaw and test its coherence, as a safety regulation, I designed a virtual airspace model. My model was 1,000 feet by 1,000 feet by 2,000 feet tall. I modeled aircraft as spheres with a radius of 50 feet. My Monte Carlo program would place aircraft in the test volume at random locations, moving in random directions. Whenever two spheres overlapped, I counted one collision, and then reset the model to do it all over again. First, I programmed spheres to obey the hemispherical cruising altitude rules. Here I summarize the regulations that were being obeyed at the moment that two aircraft collided over the Grand Canyon in 1956, killing 128 people. These were converging at an angle of 25 degrees, with both cruising level on northeasterly headings. Next, I programmed aircraft to fly at purely random altitudes with one interesting alternative. This graphic shows an alternative cruising altitude rule that I named the Altimeter Compass Cruising Altitude Rule, or ACAR. ACAR was previously invented, unknown to me, about 1928 by a long-forgotten Australian aviation safety pioneer. Not knowing anything about the 1928 Australian invention, I reinvented ACAR in 1995 for my Monte Carlo model. This relationship is visualized by a pilot imagining a compass rose superimposed on the altimeter. The 100-foot hand of the altimeter turns 360 degrees every 1,000 feet of altitude change. The pilot obeys ACAR by climbing to a cruising altitude where the heading of the 100-foot hand of the altimeter compass of the 100-foot hand on the altimeter compass rose matches the actual aircraft heading measured with the aircraft magnetic compass. This idea creates an ACAR relationship between random headings and calculated pseudo-random cruising altitudes. Head-on ACAR aircraft are automatically offset 500 vertical feet. Perpendicular aircraft are automatically offset 250 vertical feet. Aircraft converging with a 25-degree angle are automatically offset about 60 vertical feet. That offset would have saved 128 lives over the Grand Canyon in 1956. Considering the gear-up heights of these two doomed aircraft, the 1928 ACAR invention would have automatically saved them with about a 40-foot safety margin. When I say automatically, I mean with no pilot radio communications with each other or with radar-equipped air traffic controllers. No ADS-B, no ATS, no TCAS, and without even looking out the window to see and avoid other aircraft. This is a screenshot showing 6 ACAR aircraft automatically missing each other in a single 1,000-foot vertical airspace. The yellow and red tracks are for two aircraft converging at a 25-degree angle, just as with the two doomed HCAR obeying aircraft slamming into each other on Lake 21,000 feet over the Grand Canyon in 1956. If I had done a video model like this for HCAR, then all 6 would have collided, with 3 colliding at an odd 1,000-foot altitude and the other 3 colliding at an even 1,000-foot altitude. In a 1,000-foot vertical interval, there are 100 10-foot high intervals that can accommodate one small Cessna less than 10 feet high. Imagine 100 Cessnas converging simultaneously from equally spaced heading angles, all missing each other because of ACAR. Now reimagine 100 Cessnas converging simultaneously from equally spaced heading angles at two HCAR altitudes. 50 would collide at the even 1,000-foot altitude, 50 would collide at the odd 1,000-foot altitude. Contrast 100% HCAR collisions with 100% ACAR survivals in this thought experiment. What were the great-grandfathers of the current FAA experts thinking when they manufactured non-random cruising altitudes as a safety strategy? Has anyone ever seen an FAA analysis technically explaining the safety basis of the HCAR strategy? Maybe this lack of an HCAR safety basis justification is what inspired the FAA's chief scientist, Robert McCall, writing in 1975 and 1995 about the navigation paradox. The navigation paradox he describes is that pilots failing altitude-accurate station keeping, deviating somewhat above or below assigned non-random altitudes, have a better likelihood of missing a midair collision threat, compared to more skillful station keeping exactly at a formula non-random altitude, where pilots are more likely to have a midair collision. See the Wikipedia article on navigation paradox. By the way, this video simulation ran for 3 days in 2008 during an NTSB symposium on midair collision safety for drones at FAA headquarters in Washington, D.C. Twice during breaks between sessions, I talked in person for 15 minutes each to two members of the NTSB. Both members acknowledged understanding the problem of FAA's fatal flaw. Both members eventually became chairman of the NTSB. I invited the two NTSB members to visit my table with this video running continuously in a loop in that FAA headquarters conference room. Neither future NTSB chairman ever showed up to view the 30-second video. Neither future chairman ever did anything to address the FAA's fatal flaw that I explained to them in detail, showing them my peer-reviewed 1997 paper and its peer-reviewed corroborating NASA paper from 2000. This is a screenshot of my Monte Carlo program during execution. This red box shows how collision counts for 3 different cruising altitude models were compared to pure random altitude cruisers at pure random headings. The ACAR and HCAR collision counts were divided by pure random collision counts to calculate the normalized relative collision risk. Here, the FAA's HCAR fatal flaw is over 5 times more dangerous than pure random altitude cruising. Here, ACAR has about 9% fewer collisions than pure random altitude cruising. This marginal superiority of ACAR over pure random altitude cruising is earned because ACAR eliminates all head-on and angular collisions allowed by cruising at purely random headings and altitudes. Normalizing data like this puts noisy, irrelevant factors into both the numerator and denominators simultaneously to cancel each other out when the data division quotient gives the ratios in rows 2 and 6 of this table. This ratio strategy gets rid of all factors related to pilot eyesight, haze, aircraft color, see and avoid pilot due diligence, air traffic control support, and whatever else a peer reviewer might imagine to challenge these results that isolate the technical performance of the 3 cruising altitude options from irrelevant factors unrelated to the safety and efficiency of just these cruising altitude rules being compared. This screenshot shows normalized visible time to impact ratios based on recorded and averaged closing velocities for every counted collision. More visible time to impact is important because more time gives pilot more probability of detecting and evading a collision threat using the see and avoid idea. Here, HCAR provides 1.48 times more visible time than pure random flight altitudes, while ACAR provides 2.54 times more visible time to impact compared to pure random flight altitudes. In other words, ACAR is 2.54 divided by 1.48, or 1.72 times better than HCAR at providing more visible time to impact for detecting and evading a collision threat. Aircraft safety from midair collisions can be theoretically calculated by the length one airplane flies through a bunch of other airplanes before having a collision. While the formula itself has not changed since it began controlling collision probability with the Big Bang, scientists finally discovered this formula in the 1800s after performing experiments measuring how small particles blocked light. The mean free path formula that they discovered is the same formula at all size scales, from tiny radiation particles to galactic-sized targets. Naturally, airplane collision survival is directly applicable to this formula. See the Beer-Lambert law article in Wikipedia for the details of this 1800 discovery. This is the mean free path formula. It calculates the mean or average distance that a point travels in a field of finite-sized targets before having one collision. Without this formula, it's impossible to calculate the fundamental factors affecting pilots gambling on their mid-air collision risk. Notice the high school algebra simplicity of this formula. Back in high school algebra, we learned that the smaller the denominator, the bigger the quotient ratio. Therefore, cruising altitude safety demands a minimum number density of aircraft collision threat targets to maximize the level cruising length until colliding with another aircraft. The boats on a lake hemispherical cruising altitude rules manipulate pilot behavior to maximize number density in the denominator, thereby minimizing the safety calculated as the length of the cruising flight until a collision. If we had to color code collision danger arcs on our altimeters, the way we color code hazardous airspeed ranges on our airspeed indicators, this slide shows how our altimeters would be marked for HCAR and ACAR. The red bands show what we expect. Red bands show where we expect to collide with highly accurate pilots, RVSM autopilots, and drones with plus or minus 50 feet of altitude control accuracy. The orange bands show where we expect to collide with hand-flying IFR-rated pilots with plus or minus 100 feet of altitude control accuracy. The yellow bands show where we expect to collide with private pilots that are not instrument rated with a plus or minus 200 feet band of altitude control accuracy. The safest possible green bands are very small for HCAR and represent airspace that is illegal to use for cruising flight. However, the green band for ACAR cruising flight discipline goes all the way around the altimeter, protecting all pilots equally well, regardless of what compass headings they are flying. As aviators, it is our privilege and challenge to navigate in 3 dimensions. We are not constrained, like pilots of ocean sailing vessels, to navigate with all possible collision targets at the same altitude. There is no good excuse for aviators to be looking for trouble at common altitudes like boats on a lake. Under HCAR, IFR pilots fly at Lake 3,000 feet, Lake 4,000 feet, Lake 5,000 feet, and so on. VFR pilots fly on Lake 3,500 feet, Lake 4,500 feet, Lake 5,500 feet, and so on. The HCAR FARs were born as a 1963 regulatory formula with a serious birth defect. The wasted airspace in between the thin legal cruising altitudes creates flight capacity bottlenecks by the legacy use of a sorting strategy that exists only for the convenience of air traffic control, while inadvertently creating a mid-air collision safety paradox for pilots. This air traffic control sorting strategy for organizing traffic into easterly and westerly groups must be recognized as the danger that it unnecessarily creates. A drone capable of navigating the National Airspace System is on autopilot almost 100% of the time. It flies very accurately, about like humans on autopilot. With ACAR, it's possible for 10 drones to converge simultaneously over a VOR from 10 different direction heading angles that are equally spaced 36 degrees apart. And they are all likely to survive by design without contact or damage. The same 10 drones simultaneously converging over the same VOR with those same equally spaced heading angles while using HCAR, like boats on a lake, will result in the 100% guaranteed destruction of all 10 drones. The lesson learned from the mid-air collision over the Amazon jungle on September 29, 2006, between just two brand new aircraft, head-on, with GPS precision, dead center on the airway at exactly the same altitude, applies directly to my VOR crossing scenario for the 10 drones. Compare the FAA's fatal flaw with Boeing's fatal flaw, explained in the Frontline documentary by that name. The latter killed 346 in two accidents due to 737 MAX MCAS vulnerability to single failure mode accidents initiated by a component failure of a single angle of attack sensor. The 737 MAX fleet was grounded for over a year, and billions of dollars were lost waiting for a technical solution to Boeing's fatal flaw. In contrast, the FAA's fatal flaw has been killing far more, hundreds at a time, beginning in 1956 over the Grand Canyon, continuing without proper attribution of the NASA-defined administrative root cause that kills preferentially the most skillful and accurate pilots obeying a designed-to-fail safety regulation. When will the FAA issue a notice to airmen warning pilots of excessive altitude control accuracy leading to maximized mid-air collision danger when obeying HCAR altitude too closely? When will the FAA issue a notice of proposed rulemaking to correct the navigation paradox named by their own chief scientists that causes by design hazards for pilots? After my 1997 peer-reviewed article about the results of my collision counting Monte Carlo model, I personally requested a 1997 Notice of Proposed Rulemaking 28996 to fix this problem. The FAA denied my request with the peculiar rationale that my concerns do not address an immediate safety concern. After personally surviving two near mid-air collision threats that were both closing on me so fast as to be visible for less than 10 seconds before impact, whose immediate safety concern is more important? The immediate safety concern of pilots and passengers at sudden risk of death, or the immediate safety concern of a six-figure civil servant enjoying the air-conditioned comfort of a hard-walled office in FAA headquarters? How culpable are decades of FAA senior executive service civil servants for failing to apply high school difficulty physics formulas to an evaluation of design-to-fail safety rules directly implicated in the deaths of hundreds, if not thousands, of pilots and passengers around the world, caused by unsafe regulations manufacturing deaths around the world? Are the inventors of the FAA's fatal flaw protected by plausible deniability and accident reports that inexplicably fail to include the NASA-defined administrative root cause of the FAA's fatal flaw? While the FAA's fatal flaw applies around the world to airspace controlled by ICAO, EASA, and national and regional air traffic safety organizations around the world, remember this. About every other new FAA administrator claims proudly that the USA FAA is the world's leading aviation safety subject matter expert on all dimensions of aviation safety. When any nation on Earth finds the noisy data from an aircraft accident too difficult to analyze, the entire world turns to the USA FAA to apply their subject matter expertise to the root cause analysis needed to prevent future accidents. In the case of the FAA's fatal flaw killing pilots and passengers since 1956 over the Grand Canyon, and hundreds of other similar collisions from aircraft funneled into narrow slabs of airspace, that subject matter expertise seems to be bashful about serving the safety needs of pilots and passengers around the world. Why is that? See the show notes for supporting information and links under a YouTube link that looks like a ... more.